In this video, we have several key results that we have to cover. The last being Bayes' theorem, which, as far as conditional probability is concerned, is huge. It's like the result of this particular topic. But before we get there, we have to introduce a couple ideas. Some are new, and others are new ways of looking at old things. Right now, old is relative, right? We've been doing this for what, just a few weeks. Well, let's start with our definition of conditional probability. So the probability of A given B, that's the probability of the intersection of A and B divided by the probability of B, provided the probability of B is positive, right? Can't divide by 0. Well, this being an equation, we can manipulate it. We can write it in lots of different ways. So for instance, let's say I wanted to clear the fraction that's on the right? I know that there's not a 0 in the denominator here. I can multiply both sides, and then I get this result. The probability of A intersect B is equal to the probability of A given B times the probability of B, right? So the way you can sort of make sense of this is like, so on this side, this is the familiar intersection, right? The event where both A and B occur. Well, we can think of that in two ways. We could measure just the probability of B occurring, so that's this, and then multiply it by now the probability that A occurs given that we know that B has occurred. All right? So we can express the probability of this intersection as this product. And this is actually referred to as like it's a general multiplication rule, right? So I'm actually going to label that. So this is our general multiplication rule. Right? And we saw under the assumption that A and B are independent, then this simplifies even further. Because if A and B are independent, then the probability of A given B is just the probability of A. And then we have that result from a previous video, right? So there's lots that we can do with this. So we're not really going down the independent route now. We're going to focus more on this idea of conditional probability. Now, what's interesting is this probability here, right, is also, because of the commutativity property of the intersection, that probability is the same as this probability, B, the probability of B intersect A. And then if I follow this same pattern here, right? If I follow this pattern, this would be the probability of B given A times the probability that A has occurred, right? So again, right here we have these, three, well, technically four different expressions, and they're all equal just from this definition right here, right? And we will utilize the equivalence of these when we get to, Bayes' theorem, right? But before we get to Bayes' theorem, we have to have a pit stop at a result known as the law of total probability. Sounds really fancy, and I mean it is, but it's not difficult, and it ends up being extremely useful. All right, so in order to state that result and explain how it comes about, we need the concept of either, it's sometimes called a partition of our sample space, or events that are mutually exclusive and exhaustive. So lots of big words there. So let me start with a picture to give you an idea of where this comes from. So as usual, we represent our sample space with a rectangle, right? So that's our sample space. Now, pretend that this sample space is like a puzzle. And think of what it looks like when all the pieces are like, put together. You can tell where one piece ends and another one starts, but the pieces never overlap, right? The idea is that they fit together, so they never overlap, and then together they cover the entire picture or whatever image you're creating. So your puzzle pieces, they might fit together like this. Right? Some might be bigger, some might be smaller. They might be arranged in lots of different ways. But let's say we have something like that. So it's like, our sample space, sorry, is created by fitting these pieces together in such a way that the pieces never overlap, and when you put them all together, you get the entire sample space. So I'm going to label these. I'm just going to call this like A1, A2. Doesn't have to be in any particular order. Let's say A3, A4, and then I'm just going to do dot, 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 and I'm going to put AN down here, right? So again, it's like we've now broken down the sample space into these special sets, the A sub I, and they have these two properties, right? And once we have this collection of sets, I guess you could say a set of sets, right? Because that's entirely allowed. We have this special thing called a partition, right? So if A1, comma, A2, comma, AN are subsets, right, of our sample space such that, and we're going to list the two properties that are required in order to get this type of picture, right? So such that, so the first requirement is that they don't overlap. So if I take like A2 and intersect it with A3, they have nothing in common. Similarly, if I take A4 and intersect it with A1, or A4 intersected with any other set A, then they'll have no elements in common. So the first requirement is this, and this is how it's written: AI intersect AJ. That's our empty set as long as I and j are different, right? So as long as I is not equal to j. This is an important requirement, because if we don't specify this and you take a set and intersect it with itself, then it won't be empty. You'll just get back itself, right? So this is basically saying that the A's, the A sub I's, are, you can say, disjoint. And of course we know the synonym for that, the mutually exclusive. So mutually exclusive. So they can't occur together, right? So anytime like there is a particular outcome of the sample, it has to come from exactly one of these A's, right? And that's embodied in the next requirement. So the next requirement now is saying if you take A1 union with A2 union with all the A's up to A sub n, then you're going to get the entire sample space, right? So again, let's think about this. We now have these subsets of our sample space, but they have these two important properties that no two of them will ever intersect, and all of them together create the sample space. The name that we give to the second property is we say that the AIs are exhaustive, right? So they're exhaustive. So it's not that they're tired. What it is that exhaustive in the sense that they cover all the possibilities, but not as a single entity like the sample space, but individually, you have these different A sub i's, but when you take the union of all of them, all the possibilities are covered, right? So again, I do like the analogy of a puzzle where, individually, they cover just their own little section of the final image, whatever it is that your puzzle is going to end up being, and then together they form the whole, right? So if we have something like this, right, these A's, we say, right, so we say the collection of A sub 1, A sub 2, dot, 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 A sub n form a partition of S. So they form a partition of our sample space. All right, so that's the first, it's really just a definition that we need, and that's what we're defining. So some books will say you have, disjoint exhaustive sets. Others will just use the word partition, and partition implies both of these properties. All right? Okay, so now on to the next topic. So I'm going to draw, I'll make this one a little less involved as the previous one, but we still have to keep it general in order to state this result. So I'm not going to draw as many pieces, but I'm still going to label it from like A1 up to AN, right? So, you have A1, let's say you have A2, and then just do dot, 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 and then you have your A sub N. Now what I'm going to do, I'm going to draw, like we've been drawing in our Venn diagrams, I'm going to draw a single circle now, right? And that's going to represent a single event, and it's going to be B. So I'm just going to draw a single circle. Wherever it ends up, right? And this is B. So when you look at it, so when we have this other event, this single event B, do you see that it overlaps with, like a certain section of B overlaps with one part of the partition, and then another part of B overlaps with another part of the partition, and then, for instance, this part of B overlaps with this part of A1, and so forth, right? So what we can say is, again, instead of looking at B as just one event, we can look at how that event is spread across the subsets in this partition. In other words, and I'll do this with maybe a different color. I can look at that piece, right? And that is a part of B. Maybe I'll do this one kind of wavy. That's another part of B. Maybe I'll do this one dotted. That's another part of B. And then maybe I'll do this one like cross-hatched or something like that, right? So I'm using the same color to say this is one set B, but it's almost like it has been partitioned by our sets A1 through AN. So instead of just thinking of B as a whole, B can be written as, okay, take the part of A1 that intersects with B. So look at this part. So let me say it like this, like, A1 intersect B, right? And then do the same thing with A2. So again, look at this part here that intersects with B. So that's A2 intersect B. And then continue that all the way up until you get to, the nth subset of your partition. So look at where B and AN intersect. So in other words, I can write B as this complicated expression here, but it's complicated for a reason. So like this. And if, notice, each of these parts, again, they don't overlap. This is just the part that intersects with B and A1 that doesn't overlap with any of the other regions. And that's true about every set that I have in parentheses. So what I can do is I can express B as this union. So union dot 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 union, right? Again, instead of looking at the entity as a whole, you're now essentially looking at the sum of its parts, right? But it's not like numbers per se, it's sets. So we're looking again where the portion that intersects with A1, the portion that intersects with A2, all the way up to the portion that intersects with AN, and put them all together by taking the union, that gives me the whole, right? So now, this is what I can say. So let me just make the note here that all of these now, right? This intersection, this intersection, this intersection, they are disjoint. Again, the wavy part, the dotted part, the crossed part, then the striped part, they never overlap. So these are mutually exclusive, right? Or disjoint. And the reason why that's helpful is that now if I take the probability of B, it's like taking the probability of what's on the right-hand side. But because we now have the union of these disjoint events, I can take my third axiom and say that the probability of B can be written as this: the probability of A1 intersect B plus the probability of A2 intersect B plus dot 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 the probability of AN intersect B, right? So again, this is not like a huge step forward. We're using our axiom, right? Now, let's use the version of that multiplication rule that we did earlier in this video. We've done it earlier in previous videos, and I reminded you of it earlier. Is that each of these intersections now, I can write like this. So this is the same as the probability of B given A1 times the probability of A1, right? That's this part. And then the same pattern repeats for the other probabilities. So then plus the probability of B given A2 times the probability of A2, and so on until you get to the probability of B given AN times the probability of AN, right? And we can actually write this using our sigma notation since it's a sum, right? So therefore, the probability of B, this one little event, we've now, made it look so complicated, but it's complicated for a reason, right? So I'm going to use K. Let's say K is going from 1 to N. And what is the pattern? Well, it's the probability of B given A sub K times the probability of A sub K, right? So again, with this concept of a partition, we can take a single event and break it up into these pieces. And you might wonder, why would we want to do that? It's because many times we might know the individual pieces that fit together to give us the whole, right? So we don't know the whole right away. What we know are the individual pieces, and this particular result allows us to figure out the whole. So problems that are related to this concept you have this information given to you, and you're asked to find something like this, right? And this is the law of total probability, right? So this is the law of total probability, right? In other words, for B to occur, those events that it overlaps with in the partition has to occur as well. All right? Okay. So that's so now let's take a look at how we might use something like this. And what I'm going to do is write up a quick example talking about urns, right? So here's an example, and I'll try not to make it too wordy. So let's say we have two urns. Say urn 1 and urn 2. And and in each urn we have a certain number of red chips and a certain number of blue chips. So I'm literally going to draw them. So 1, 2, 3, and then let's say 1, 2, 3, 4. So in urn 1 we have 3 red and 4 blue. And in urn 2, let's say we have 2 red and 3 blue, right? And so the game is this. We are going to choose one of the urns at random, right? And then we're going to choose one of the chips from the urn that we've chosen. We will then choose one chip. So this experiment now has essentially 2 stages to it, right? And that's why there's a little bit more that goes into the analysis. So here's our, let's call it a game. The games are fun, right? So game, choose an urn at random. So like you're blindfolded, right? Nice party game. So choose an urn at random and then choose a chip at random from that urn. Right, so and then choose a chip at random from that urn. All right? And here is the question. Let's say, what is the probability that we get a blue chip, right? So that's the question. So what is the probability of getting blue? Okay, right. Well, so let's say that. So now, when we say like choose an urn at random, usually that means there's a 50% chance, right? So there's a 50% chance that you'll choose urn 1 versus urn 2. But let's say that in practice, like if you actually did this, let's say that it wasn't 50% of the time that you choose urn 1 or 50% you choose urn 2. So let's assign some probabilities here. So suppose the probability that you choose urn 1 is 1/3, and therefore the probability of choosing urn 2 would have to be 2/3, right? It's one or the other, right? It's one urn or the other. Now let's look to see the likelihood of getting a blue from each of these, right? So remember what we have. So if we were to choose urn 1, right? Then we would have a 4 out of 7 chance of getting a blue, right? So, but that's a conditional probability. Given that we choose urn 1, the probability of getting a blue is 4/7, right? And similarly, if we were to choose urn 2, we have a probability of 3/5 of getting a blue, right? So then the probability of a blue given urn 2, that's 3/5, right? So in terms of the the partition here are the two urns, right? Like these chips are different from these chips, and together they form your entire sample. Our entire sample in this case is a total of 7 plus 5, so 12 chips. But they're not equally distributed between the urns, and similarly, the likelihood of picking one urn over the other, again, I've assigned these probabilities of 1/3 to 2/3, right? So let's see if we can figure out the answer to this question, right? So in fact, yeah, let me write this down, just making sure that we can say that these two form our partition, right? And so let's apply our law of total probability, right? So this is what it says. So the probability of getting a blue, again, there are two ways that can happen. We can write that as a probability of getting a blue given that you've chosen the first urn times the likelihood that you will choose that first urn plus the probability of getting a blue given that you've chosen the second urn times the likelihood of choosing that second urn. Right? And since we have these four probabilities, it's just a matter of plugging in and simplifying. So let's see what we have. So over here, so the probability of B given the first urn, that's 4/7. So there are 4 blue out of a total of 7 in that first urn. The likelihood of assigning, or of choosing that first urn is 1/3, right? And then the probability of getting a blue given that we choose the second urn, that's 3 out of 5, so 3/5. And we will choose that second urn, 2 out of 3 times, so 2/3. So putting this together, we will have, what's this, 4/21 plus, in fact, this reduces to 2/5. And if we get a common denominator of, what would that be? Well, I guess we could use 105. So if we have 105 there, multiply the top by 5, that's 20. And then plus, again, 105 here, multiply the top by 21, we get 42. And then we end up with a probability of 62 out of 105. And again, if you want, you can turn this into a percent, right? But this is the likelihood of us, again, choosing an urn at random based on these probabilities, right? And then picking a chip out of the urn that we've chosen by, if we were to perform those two steps, given this likelihood of, the measure of choosing a particular urn, then the probability of us getting a blue chip is 62 out of 105. All right. So you can see that the type of experiment now, it's a little bit more complicated. There are two levels of randomness. Which urn are we going to choose, right? And then which chip out of that urn are we going to end up getting? All right, so that's the law of total probability, and very, very useful. And what it allows us to do now is finally talk about our Bayes' theorem. So let's see what Bayes is all about. And again, let me start with a graph or a picture of our sample space. And again, with our partition. And now, again, let me draw B. So here is B. Now, here is another important question, very important question. And the question is this: if we know that B has occurred, right? So if B is known to occur, right? What is the likelihood that the elements came from A1? Or what is the likelihood that the elements came from A2 or AN or any of the A's, right? If B is known to occur, the other question is, what is the probability that any of the given A's have also occurred, right? So what is the probability that any A sub I has occurred, right? And that's a conditional probability, right? So if we set it up, so let's go through what we know now, and this is where we put it all together, folks, all together. So let's write down what the question is. So it says, given B, what is the probability that AI has occurred? That's what we want to find. Well, we have a definition for this. We have a definition for this conditional probability. It is the probability that AI will intersect with B divided by the probability of B, right? Now, when we started, we said that this, and let me write it again, this is the same as the probability of B intersect AI, right? Because that's one of our properties of the intersection. And then this can be written as the probability of B given AI times the probability of AI. So this is what we did when I just kind of reminded you earlier of the definition of conditional probability, and that we can write these two in different ways, right? Right. So, and make sure that this is a times, right? So that's what we can do with the numerator. With the denominator, we just did the law of total probability. We're saying that this thing in the bottom can be written as the sum of k going from 1 to n of the probabilities of B given the A sub k times the probability of A sub k, right? You know, so we have all these things. We have our conditional probability in the numerator over here, and then we have our law of total probability in the denominator. So Bayes, which I believe he was like a British pastor or something. How did he come up with this? Maybe he had some divine intervention, right? But the thing is, so again, if we now want to ask ourselves this question, we know that B has occurred. What is the likelihood that it came from a particular element of the partition, right? So one of our sets in the partition. Well, here is Bayes' formula. And it looks complicated, right? But the numerator now, notice that the roles are flipped. In the numerator, it's the probability of B given AI times the probability of AI. And then, so this is one of the terms that are in this summation, right? In the denominator, it's not just this particular one, but it's all the terms of that form added together. So it's the sum as k goes from 1 to n of the probability of B given A sub k times the probability of A sub k. And this is the famous well, I don't know if you've heard about it before, but I can tell you in the world of probability and also in statistics, Bayes' theorem is king as far as conditional probability is concerned. So this is Bayes' theorem, right? And it's essentially just taking everything that we've done apart from the independence, so going back to conditional probability, now this concept of total probability, putting it all together and getting this particular result, right? So what we will do, we will end this video now, and in the next video we will spend time just doing a couple examples that will utilize Bayes' theorem. But here's the cool thing that you have to look forward to. I will give you a visual way of setting these problems up. So yes, this this formula, it looks messy, it looks scary, but again, there is a tool that we can use that will allow us to visualize how all this fits together and makes the problem solving a whole lot more efficient. So I know you can't wait to see that, so why not just start the next video right now. See you then.